Okay, so at the end of the last video, we were looking at enthalpy of solution, and we said that delta H solution was equal to minus delta H lattice plus delta H hydration. In other words, we need to break up the lattice and then we can hydrate the ions, and that gives us the enthalpy of solution. We also said that if this enthalpy of solution was negative, in other words, if it was an exothermic reaction, it was more likely to be soluble. Now we have an issue therefore with something like sodium chloride, NaCl, better known as table salt, because its enthalpy of solution is positive. It's about plus 3 kilojoules per mole. And yet we do know that sodium chloride is very soluble. So there must be something else going on, and that something else is entropy. Because if you think back to your entropy notes, you'll remember that if the total entropy change is positive, then the reaction is feasible, and that's what determines the feasibility of the reaction. Okay, so our delta S total is equal to our delta S system plus our delta S surroundings. Now we know from this reaction that because we've got an endothermic enthalpy change here, this delta S surrounding term will be negative because it's a positive here. Now, in order for this reaction to work, in order for this value here to come out as positive, we have to get this delta S system to be positive and to be larger than this negative. So we want this delta S system value to be a larger positive value than this surroundings is a negative value. And if we look at the equation, we've got sodium chloride, solid, dissolving in some water to make sodium aqueous ions and chloride aqueous ions. And we can see quite clearly from this that we are going to get a positive delta S system in terms of the ionic lattice. Here you've got this solid ionic lattice and it's dissolving to form two aqueous ions. So the entropy is significantly increasing because you're going from 1 mole of solid to 2 moles of aqueous ions. So that does make this a large positive value, and certainly large enough to outweigh this small negative, because it's only just endothermic, which gives you a delta S total here which is positive, and therefore the reaction is feasible. So now we need to look at magnesium carbonate. So magnesium carbonate, MgCO3, has a negative enthalpy of solution. It is minus 13 kilojoules per mole, and yet is insoluble in water. So we need to explain what's going on there. So looking again at our entropy equation, delta S total is equal to delta S system plus delta S surroundings. Now we know it's an exothermic reaction, so that's going to make this delta S surrounding term positive. But in order for this delta S total to be negative, therefore this system term has to be a negative value, and it has to be a larger negative than this is positive. So again, we're going to look at the equation. So I've got magnesium carbonate this time, dissolving in water, or not dissolving in this case, to form magnesium carbonate. That's magnesium ions and carbonate ions, 3,2 minus, aqueous, all floating around the place. Okay, now the solids is going into the two aqueous ions, so there's definitely an increase in entropy there, so that gives me a positive entropy change. But yet overall the whole thing comes out as a negative entropy change. We need to consider why that is. The solid is going to two aqueous ions. That's definitely a positive change. But there's one thing we haven't considered, and that's what's happening to the water. This comes back to something we looked at earlier. So here we have our magnesium ion from our magnesium chloride, and here we have our sodium ion from our sodium chloride. Now here, the magnesium ion attracts a lot of water molecules, but if you notice, they're not randomly arranged around that magnesium ion. They're particularly orientated so that the negative end, the oxygen, is pointing towards the 2+, and the hydrogens are pointing away from it. So these water molecules are becoming ordered. Because magnesium is a small and highly charged ion, it can order those water molecules quite strongly. Whereas sodium, on the other hand, can't organise the water as efficiently. So you get less ordered water around the sodium ion because it's too large. So this explains why this reaction overall has a negative delta S system. The lattice is increasing in entropy, but the water is decreasing in entropy because the water is going from a random arrangement of water molecules to this more ordered structure here, where those water molecules are orientated around this small positive. We say that magnesium has a hydration number of 29, so it can order a lot of water molecules, whereas the sodium only has a hydration number of 13. So it is this ordering of the water that causes this value to be negative, and it's a large enough negative to outweigh the small positive here to turn delta S total negative overall, and therefore this reaction is not feasible. Okay, so that takes us through the last bit of theory in these notes. So you're going to need to read page 11 very carefully. You're going to need to think about it and possibly watch the video over again so you're absolutely confident in explaining why substances like sodium chloride, despite them having an endothermic enthalpy of solution, are soluble, and why substances like magnesium carbonate, despite them having a negative enthalpy of solution, are insoluble. What we'd like you to do now is the questions at the end of the topic and have everything uploaded for Friday. As usual, if you've got any questions or queries, please email me or contact me through Teams. Take care, stay safe, speak to you soon. Bye bye.